A man dies in 1691, and the world barely notices. 8 days earlier, his sister passed away in the same London house where they'd lived together for 3 decades. Within a week, he's gone too. No grand funeral procession, no state ceremony, just a quiet burial and a modest stone. But here's what nobody realised at the time. This man had already rewritten the rules of reality itself. Robert Boyle didn't just discover scientific laws, he invented the modern idea of what science is. Before him, natural philosophy was a gentleman's hobby, a pastime for aristocrats, dabbling in curiosities between hunting trips. After him, it became something else entirely, a systematic method for interrogating nature, a discipline that demanded evidence over authority, experiment over tradition. He took the medieval worldview, the one that had dominated Europe for 1,000 years, and demolished it with a glass tube and some mercury. But the story doesn't start with laboratories or discoveries. It starts with obscene wealth, political chaos, and a childhood spent learning that nothing in life is stable. January 25th, 1627. Lismore Castle, County Waterford, Ireland. A massive stone fortress overlooking the Blackwater River, home to one of the richest men in the British Isles. Richard Boyle, the Earl of Cork, is in his 60s. His wife Catherine is in her 40s, and they've just had their 14th child. Think about that for a moment. 14th child. In an era when childbirth regularly killed mothers and half of all children died before age 10, the Boyles kept producing offspring like it was their main occupation, which, for aristocratic families, it essentially was. You needed heirs, backups for the heirs, and backups for the backups. The Earl of Cork took this strategy to extremes. Robert was the 7th son, which meant he'd never inherit the title or the main estates. That was reserved for the eldest surviving son. But he'd still be wealthy, still be educated, still have opportunities most people couldn't imagine. The question was what he'd do with them. His father's story is worth understanding because it shapes everything that follows. Richard Boyle arrived in Dublin in 1588 with almost nothing. He was English, ambitious, and willing to do whatever it took to succeed in a country England was actively colonising. Ireland in the late 1500s was a landscape of opportunity for English settlers. Native Irish landowners were being displaced, their properties seized and redistributed to loyal English subjects. It was brutal, systematic, and enormously profitable if you knew how to work the system. Richard Boyle worked it better than almost anyone. He secured a position as a deputy esquiter, the official responsible for managing properties that reverted to the crown when owners died without heirs. It was the perfect position for someone with flexible ethics and sharp instincts. Within years, he'd accumulated vast landholdings across southern Ireland. By the time Robert was born, the Earl of Cork controlled more territory than some small kingdoms, but wealth in 17th century Ireland was precarious. You held land through force and political connections, not legal certainty. The native Irish population resented the English colonisers. Catholic-Protestant tensions simmered constantly, and England itself was sliding towards civil war. The world Robert Boyle was born into was one where fortunes could vanish overnight, where political allegiances determined survival, where nothing felt permanent except uncertainty. His mother died when he was 4. Tuberculosis took Catherine Boyle in February 1630, leaving behind 12 surviving children and a husband who'd lost his partner of decades. Robert barely knew her. In aristocratic families of the era, children were raised by wet nurses and servants, not parents. You saw your mother occasionally, formally. When she died, it was sad, but not the devastating loss it might be in a closer family structure. What he did know was his father, and Richard Boyle cast a long shadow. Tall, thin, pale face, large eyes. Contemporaries described him as intensely intellectual, scholarly, bringing unusual energy and determination to everything he attempted. Robert inherited the same physical build, the same temperamental intensity. Father and son looked alike, thought alike, approached the world with the same combination of curiosity and relentless drive. Richard Boyle believed in education, but not the coddled aristocratic version. He sent his younger children to live with poor families in the Irish countryside during their early years. The theory was that hardship made you stronger, that comfort bred weakness. Whether this actually worked is debatable, but it definitely gave Robert a stutter that would plague him for life. Spending your formative years with people who spoke different languages in conditions far below your family's status apparently does things to a child's speech patterns. At 8 years old, shortly after his mother's death, Robert and his brother Francis were sent to Eton College in England. Their father had connections there. Sir Henry Wotton, the provost of Eton, was a friend, and Eton was where England's elite educated their sons, preparing them for university and eventual positions of power. The education was classical, brutal and thorough. Latin dominated everything. You studied it for hours every day, memorizing vast passages from ancient authors, Cicero, Virgil, Ovid, Horace. You learned to read, write, speak and think in Latin, because that was the language of educated Europe. English was for commoners, French was for diplomacy, but Latin was for serious intellectual work. Greek came next, though less extensively. Geometry, rhetoric, logic, theology. The curriculum hadn't changed much in 200 years. It was designed to produce gentlemen who could quote classical authors, construct proper arguments, and navigate the social hierarchies of church and state. Physical punishment was routine. Masters believed the rod was essential to learning. You memorized your declensions or you got beaten. Simple as that. Robert survived Eton, but he wasn't a star student. Competent, nothing more. The endless rote memorization bored him. The classical focus felt disconnected from the world he saw around him. But he learned Latin fluently, absorbed the rhetoric and logic, developed the intellectual foundation he'd need later. Whether he enjoyed it is another question entirely. Then at age 12, everything changed. His father had a plan for his younger sons, one that would shape Robert's entire trajectory. The Grand Tour. This was a tradition among wealthy English families. You sent your teenage sons on an extended trip through continental Europe, exposing them to foreign cultures, languages, art and ideas. The theory was that travel broadened the mind, that experiencing different societies made you more sophisticated, more capable of navigating international politics and commerce. In practice, it was often just an excuse for aristocratic teenagers to spend a few years drinking wine, chasing women, and occasionally looking at paintings. But Richard Boyle took it seriously. He hired Isaac Marcombes, a renowned Swiss tutor who'd successfully guided his older sons through similar tours, and sent Robert and Francis off in 1639. They travelled from England to France, landing at Dieppe before making their way to Paris, then south to Lyon, and finally to Geneva, where they'd spend most of the next few years at Marcombes' home. Geneva wasn't chosen randomly. It was a Protestant city, a refuge for Huguenots fleeing Catholic persecution in France, and a centre of Calvinist theology. For a devout Protestant family like the Boyles, it was the ideal location. Marcombes was more than a tutor. He was a Huguenot who'd fled France for religious reasons, married to the niece of Giovanni Diodati, a famous Genevan preacher who translated the Bible into Italian and French. The household was intensely religious, rigorously intellectual, and deeply committed to the Reformed Protestant tradition. Robert studied French, Latin, Italian. He learned geometry, Roman history, philosophy. He took fencing lessons, practiced tennis, learned to ride horses properly. The curriculum was broad, practical, designed to produce a well-rounded gentleman capable of functioning in any European court or commercial centre. But the most important education happened in church. Marcombes took the boys to services twice weekly, read to them daily from the Bible, and Calvin's Catechism. And one night, in 1641, during a terrible storm, Robert Boyle had an experience that would define the rest of his life. He was 14 years old, alone in his room, when thunder and lightning turned the Geneva night into chaos. The storm was violent, terrifying, the kind that makes you think the world is ending. And Robert, raised on Protestant theology, with its emphasis on divine judgment and human sinfulness, became convinced that this was it. The day of judgment had arrived. He thought about his life so far, the privileges, the education, the comfortable existence, and he felt it had all been wasted on trivial pursuits. He hadn't done anything meaningful, hadn't served God or humanity, hadn't justified the gifts he'd been given. So he made an oath. If God allowed him to survive this night, he would dedicate himself to Christian service. He would use his life for something beyond personal pleasure or advancement. The storm eventually passed. Morning came, and Robert, to prove his sincerity, repeated the oath in daylight. Whether God was listening is a theological question. What matters is that Robert believed it absolutely. For the remaining 50 years of his life, he saw himself as someone who'd made a covenant with the divine. His work, his studies, his experiments, all of it was in service of that teenage promise made during a Geneva thunderstorm. The oath had another consequence. Robert developed a lifelong aversion to swearing oaths. He'd made his promise to God, and that was enough. Later, when offered prestigious positions that required formal oaths of office, he'd refuse them. Not out of disrespect, but because he took the act so seriously that he couldn't repeat it. The Grand Tour continued. In 1641, Robert learned Italian in preparation for visiting Italy. By September, he and Mark Holmes were in Venice. By early 1642, they'd reached Florence. Florence was where everything crystallized. Because in January 1642, while Robert Boyle was living in the city, Galileo Galilei died at his villa in Arcetri, just outside Florence's walls. Galileo was 77 years old, blind, under house arrest, by order of the Roman Catholic Inquisition. 9 years earlier, he'd been tried for heresy, forced to recant his support of Copernican heliocentrism, the idea that the Earth orbits the Sun rather than sitting motionless at the centre of creation. He'd spent the last decade of his life confined to his home, forbidden from teaching or publishing. Robert Boyle never met him. They'd hoped to visit, but Galileo died before they could arrange it. But Robert studied his works intensively, reading everything he could find in Italian. And what he read changed how he saw the universe. Galileo argued that mathematics was the language of nature, that the physical world operated according to precise, mechanical laws that could be discovered through observation and measurement, that authority, tradition, and ancient text didn't matter compared to what you could demonstrate through experiment. This was revolutionary. For over 1,000 years, European natural philosophy had been dominated by Aristotle's teachings, interpreted through Catholic theology. You learned about the world by reading ancient texts and reasoning from first principles. Observation was secondary, experiment was barely considered. The idea that you could interrogate nature directly, force it to reveal its secrets through systematic investigation, was almost unthinkable. But Galileo had done exactly that. He'd built telescopes and observed the moons of Jupiter. He'd studied falling bodies and discovered laws of motion. He'd challenged religious authority with evidence, and though the church had silenced him, his ideas were spreading across Europe. For a young Protestant like Robert Boyle, this had special resonance. His religious background included an ingrained suspicion of Catholic authority, a belief that the Roman Church had corrupted Christianity with its emphasis on tradition and hierarchy over scripture and individual conscience. Seeing Galileo persecuted by that same church for promoting ideas based on observation rather than doctrine confirmed everything Robert had been taught about Catholic corruption. More than that, it gave him a mission. If natural philosophy could reveal God's design, if studying creation could illuminate the Creator's wisdom, then scientific investigation wasn't just intellectually interesting. It was a religious duty. The Storm Night Oath and Galileo's example fused into a single conviction. Robert Boyle would dedicate his life to understanding nature through systematic experiment, and in doing so, serve both truth and God. But first he had to get home, because while Robert was absorbing Italian culture and Galilean philosophy, England was tearing itself apart. His father died in 1643, leaving behind a complex estate and a country descending into civil war. The grand tour ended abruptly. Robert had to return to a nation where choosing the wrong side could cost you everything. Robert Boyle arrived back in England in 1644 to find a country he barely recognised. He was 17 years old, his father was dead, and the nation was at war with itself. The English Civil War had erupted in 1642, pitting King Charles I against Parliament in a conflict that was simultaneously about power, religion, taxation, and the fundamental question of who ruled England. By the time Robert returned, battle lines had hardened, armies were marching across the countryside, towns were choosing sides or being forced to choose, families were splitting apart. Robert's family had chosen Parliament. His father had fought for it during the early stages of the conflict. Several of his brothers were involved in the parliamentary cause. This wasn't a neutral inheritance. Coming home meant stepping into a political identity, whether he wanted it or not. But Robert didn't go to war, he went to Stalbridge. Stalbridge was a manor house in Dorset that his father had left him, a sizable estate in the English countryside. It was isolated, relatively safe, and exactly what Robert needed. Because while England tore itself apart over politics and religion, Robert Boyle had something else on his mind. He wanted to understand how the world worked. The young man who settled at Stalbridge in 1644 was changed from the boy who'd left for Geneva 5 years earlier. The Storm Night conversion had given him purpose. Galileo's example had given him method. His father's death had given him independence and wealth. Now he had space to figure out what to do with all of it. He started writing. His first project was a moral treatise called Aretology, an ethical work exploring virtue and proper conduct. It was earnest, somewhat clumsy, the kind of thing a serious young man writes when he's trying to work out what he believes. He never finished it, but the effort mattered because it showed him what he didn't want to be. Robert didn't want to be a moral philosopher writing abstract treatises. He wanted to be an experimental philosopher investigating nature directly. The problem was that in 1640s England, there was no clear path for becoming that. Natural philosophy existed, but it was mostly theoretical, conducted by university scholars debating Aristotelian principles. Alchemy existed, practiced by secretive individuals pursuing transmutation and spiritual enlightenment through obscure processes. But systematic experimental investigation, the kind Galileo had pioneered, that was barely getting started. Robert began equipping a laboratory at Stalbridge around 1646 or 1647. He bought equipment, chemicals, furnaces. He started conducting experiments, trying to replicate processes he'd read about, testing ideas, learning through trial and error. He had no formal training in this. He was teaching himself, which meant he made mistakes, destroyed equipment, occasionally produced results he didn't understand. But he kept going, and he started making trips to London. London was where the action was, not the military action, though armies sometimes came near the city, the intellectual action. Because something remarkable was happening in the capital, something that would change Robert Boyle's life, and eventually change science itself. A group of men had started meeting regularly to discuss natural philosophy. They called themselves various things at different times, but Robert, in his letters, referred to them as the Invisible College. This wasn't an official institution. It had no building, no charter, no formal membership. It was just a network of people interested in the new experimental philosophy, meeting wherever they could, sharing ideas, conducting demonstrations, arguing about methods and results. The composition varied. Some were physicians, some were interested gentlemen, some were clerics. What united them was curiosity about nature and a shared conviction that the old ways of understanding the world, reading Aristotle and reasoning from first principles, weren't enough. You had to observe, you had to experiment, you had to test. Robert discovered them during one of his London visits, probably around 1646. He was 19 years old, the youngest member, and he was absolutely captivated. In letters to his former tutor, Isaac Marcombes, now back in Geneva, Robert described the Invisible College with barely contained excitement. These people were doing what he wanted to do. They were investigating air pressure, studying anatomy, examining chemical reactions, building instruments, collecting observations. They were taking Galileo's approach and applying it systematically across every domain of natural philosophy, and they welcomed him. Despite his youth, despite his lack of formal university training, they recognized his intelligence and his commitment. More importantly, they recognized his money. Experimental philosophy required equipment, and equipment required funding. Robert had both the interest and the resources to support the work. He became a regular participant, travelling to London for meetings, conducting experiments at Stalbridge, and reporting results, corresponding with members who lived elsewhere. The Invisible College gave him something crucial that he couldn't get from books. It gave him a community of people who understood what he was trying to do and why it mattered. But Stalbridge had limitations. It was isolated. Equipment was hard to obtain. Skilled assistants were nearly impossible to find in rural Dorset. The laboratory Robert could build there was impressive for a manor house, but it couldn't compare to what was possible in a university town, with access to craftsmen, suppliers, and other natural philosophers. Robert needed to be somewhere with better infrastructure, somewhere with people who could help him build more sophisticated apparatus, somewhere with intellectual stimulation beyond occasional trips to London. He thought about Oxford. The university was one of England's two great centres of learning. It had libraries, learned men, and a tradition of philosophical inquiry. But it also had problems. The Civil War had disrupted everything. Royalist sympathisers among the faculty had been purged and replaced with parliamentary appointees. The atmosphere was politically charged and intellectually uncertain. Still, Oxford had resources. And in 1652, after spending 2 frustrating years trying to manage his Irish estates, Robert decided to make a change. He accepted an invitation to come to Oxford, not as a formal student or faculty member, but as an independent scholar with his own means who could set up his own laboratory and work as he pleased. He arrived around 1655 or 1656, now in his late 20s, wealthy enough to rent good lodgings and equip a proper laboratory, and he immediately began attracting attention. Part of it was his status. The son of the Earl of Cork, dedicating himself to experimental philosophy rather than politics or court life, was unusual enough to be interesting. Part of it was his approach. Robert was systematic, careful, and willing to publish his results with meticulous detail. He wasn't protecting secrets or claiming special knowledge. He was sharing methods so others could verify and build on his work. And part of it was simply that Oxford, in the 1650s, was full of brilliant people, and Robert Boyle fit right in. He became associated with what was called the Experimental Philosophy Club, a group that met regularly, sometimes in Robert's own lodgings. The membership included John Wilkins, who would later help found the Royal Society, Christopher Wren, who would become England's greatest architect after the Great Fire of London, John Locke, who would revolutionize political philosophy. These weren't just colleagues, they were friends, collaborators, people who shared Robert's conviction that natural philosophy needed to be rebuilt from the ground up through systematic investigation. But Robert needed something more than brilliant colleagues. He needed skilled hands. He needed someone who could build the intricate apparatus required for his increasingly ambitious experiments. Someone who understood mechanics, who could solve practical problems, who could turn theoretical designs into working instruments. In 1655, he found that person. A young man with extraordinary mechanical abilities and no money to continue his studies. His name was Robert Hooke. Hooke was maybe 20 years old when Boyle hired him as an assistant. He'd been a student at Oxford, showing remarkable talent for constructing scientific instruments, but he lacked the funds to complete his degree. Boyle offered him paid work in his laboratory. It was one of the most productive partnerships in the history of science. Hooke could build anything. Give him a design, he'd construct it. Give him a problem, he'd engineer a solution. He had an intuitive understanding of mechanical principles, an ability to see how parts could fit together, how forces could be balanced, how apparatus could be made to work reliably. And Boyle had ideas that desperately needed someone with those skills. Because Robert had become obsessed with a particular question. What was air? What were its properties? How did it behave? Could you remove it and create a vacuum? This wasn't idle curiosity. Understanding air was central to understanding how the world worked. Combustion happened in air. Animals breathed air. Sound travelled through air. Weather was air in motion. But nobody really understood what air was or how it behaved under different conditions. Some philosophers claimed a vacuum was impossible, that nature abhorred emptiness and would always rush to fill any void. Others argued you could create a vacuum but debated what would happen inside it. Would candles burn? Would animals survive? Would sound propagate? These weren't just theoretical questions, they were testable. If you could build an apparatus that removed air from a sealed container, you could run experiments and see what happened. You could turn philosophical speculation into empirical knowledge. The problem was building that apparatus. Creating and maintaining a vacuum required sophisticated mechanical equipment, a pump that could remove air, a vessel that could remain sealed under pressure, instruments that could measure what was happening inside. Several natural philosophers had already tried. Otto von Guericke in Germany had built an air pump and conducted public demonstrations showing that evacuated hemispheres couldn't be pulled apart, even by teams of horses. But his apparatus was large, crude, difficult to operate. It was more a demonstration device than a precision instrument. Boyle wanted something better. He wanted an air pump that could be operated reliably, that would allow him to conduct controlled experiments, that could produce results other natural philosophers could verify. He sketched designs. Hooke built prototypes. They tested, failed, redesigned, rebuilt. It took years. By 1659, they had it. A working air pump, or as they called it, a pneumatic engine. It wasn't perfect. The seal leaked. The pump was exhausting to operate. The glass receiver sometimes cracked under pressure. But it worked well enough to conduct systematic experiments. And that's exactly what they did. From spring through fall of 1659, Boyle and Hooke performed experiment after experiment. They put candles in the receiver and pumped out the air. The flames died. They put small animals in the receiver. The animals suffocated when the air was removed. They rang bells inside the evacuated space. No sound emerged. They placed containers of water inside. The water boiled at room temperature when pressure decreased. Each experiment revealed something about air's properties. Air was necessary for combustion. Air was necessary for life. Air was necessary for sound. Air pressure affected boiling points. These weren't just observations. They were systematic demonstrations that could be repeated, measured, and built upon. Robert wrote it all up in meticulous detail. His book, New Experiments Physico-Mechanical, Touching the Spring of the Air and Its Effects, was published in 1660. It described 43 experiments, providing exact procedures, careful observations, and thoughtful interpretations. The response was immediate. Some praised it as groundbreaking work. Others attacked it, arguing that his vacuum wasn't really empty, that his interpretations were wrong, that he'd made errors in reasoning or procedure. Robert welcomed the criticism, not because he enjoyed being attacked, but because it meant people were taking experimental philosophy seriously enough to argue about it. They were engaging with evidence, debating interpretations, suggesting alternative experiments. This was exactly how natural philosophy should work. One critic in particular pushed Robert to go further. A Jesuit named Franciscus Linus argued that the air pump didn't create a vacuum at all. Instead, Linus claimed an invisible funiculus, or thread, stretched between the walls of the container when air was removed, holding things in place through some kind of tension. Robert thought this was nonsense, but to prove it, he needed more evidence. So he and Hooke designed new experiments, including one that would become famous for reasons they didn't initially anticipate. They took a glass tube, sealed at one end, and filled it with mercury. Then they inverted it into a basin of mercury, keeping the open end submerged. The mercury in the tube dropped, but not all the way. It settled at a height of about 30 inches, leaving empty space at the top of the tube. Why didn't all the mercury flow out? Why did it stop at that particular height? And what was in the space above it? By varying the experiment, adding more mercury, using different amounts, Robert noticed something crucial. The height of the mercury column and the volume of the space above it changed in a precise, predictable way. When you doubled the weight of mercury pressing down, the space above compressed to half its original volume. Triple the weight, the space compressed to 1/3. The relationship was exact and mathematical. This wasn't just about mercury in tubes. This was a fundamental law describing how gases behave under pressure. And it was the first physical law in history to be expressed as a precise mathematical equation relating two variable quantities. Robert published these results in 1662. Today we call it Boyle's law, and it's taught in every chemistry class. But at the time, it was revolutionary, because it demonstrated exactly what Galileo had argued. Nature followed mathematical laws. You could discover those laws through careful experiment, and once discovered, they could be expressed with precision and used to predict phenomena you hadn't directly observed. This was the new philosophy in action. Not speculation, not appeals to ancient authority, not theological reasoning. Evidence, measurement, mathematics, systematic investigation, producing reliable knowledge about how the natural world actually behaved. And Robert Boyle was just getting started. The success brought problems Robert hadn't anticipated. Fame attracted attention, and attention meant scrutiny. Critics emerged from everywhere, questioning his methods, his conclusions, his entire approach. Some were legitimate scientific disagreements. Others were personal attacks disguised as intellectual debate. Thomas Hobbes was perhaps the most formidable opponent. Hobbes was a philosopher, a mathematician, and a man who believed natural philosophy should be deduced from first principles through pure reason. The idea of learning about nature by poking at it with instruments struck him as absurd. He wrote a blistering critique of Robert's air pump experiments, arguing that the whole enterprise was based on faulty assumptions. Robert responded with a book, not a short pamphlet, but a detailed systematic defense of experimental philosophy titled A Defense of the Doctrine Touching the Spring and Weight of the Air. He addressed every objection Hobbes raised, explained why experiments were necessary, and demonstrated why pure reasoning without evidence could lead you astray. The debate got heated. Hobbes doubled down. Robert wrote more. Back and forth they went, each convinced the other was fundamentally wrong about how to study nature. But here's what's interesting. The argument itself advanced the field. By forcing Robert to defend his methods explicitly, Hobbes inadvertently helped establish the principles of experimental science. Robert had to articulate exactly why experiments mattered, why evidence trumped theory, why you couldn't just think your way to understanding the physical world. While this philosophical battle raged, Robert kept experimenting. He wasn't content with air pressure and vacuums. He wanted to understand matter itself. What were things made of? How did substances transform into other substances? These were questions alchemists had pursued for centuries, usually while searching for ways to turn lead into gold. Robert approached them differently. In 1661, he published The Skeptical Chemist. The title was deliberate. He was skeptical of the theories everyone else accepted without question. Aristotle claimed everything was made of 4 elements: earth, air, fire, and water. Paracelsus, a famous physician and alchemist, argued for 3 principles: salt, sulfur, and mercury. Robert thought both were wrong. His argument was radical. Elements weren't philosophical categories or mystical principles. They were physical substances that couldn't be broken down further. If you could separate something into simpler parts, it wasn't an element. If you couldn't, maybe it was. The definition sounds obvious now. It wasn't obvious then. He also proposed something even more fundamental. Matter, he argued, was made of particles, tiny corpuscles that moved and collided and combined in various ways. Different substances had different properties because their particles had different shapes and motions. Chemical reactions happened when particles rearranged themselves into new configurations. This was corpuscular philosophy, and it would eventually evolve into atomic theory. But Robert wasn't just speculating. He was trying to explain experimental observations. Why did some substances mix while others didn't? Why did heating things change their properties? Why did acids and alkalis neutralize each other? Particles in motion provided answers. Not everyone accepted this. Plenty of natural philosophers still clung to Aristotelian elements or Paracelsian principles. But the skeptical chemist planted seeds. It made people question assumptions. It showed that you could approach chemistry systematically, experimentally, looking for underlying patterns rather than accepting traditional categories. The work was exhausting. Robert's health, never robust, began deteriorating. His eyesight weakened to the point where reading became difficult. His hands trembled, making it hard to perform delicate experiments. He suffered recurring illnesses that left him bedridden for weeks at a time. He adapted. He hired assistants to read aloud to him. He dictated his writing rather than penning it himself. He designed experiments other people could execute while he supervised. The work continued, slower perhaps, but uninterrupted. His laboratory in Oxford became a hub of activity. Students and visitors came to watch demonstrations, discuss theories, argue about results. Robert welcomed them all. He believed knowledge should be shared, not hoarded. He published detailed descriptions of his experiments so others could replicate them. He corresponded with natural philosophers across Europe, exchanging ideas and techniques. This openness was unusual. Many experimenters guarded their methods jealously, afraid competitors would steal their discoveries. Robert saw it differently. Science progressed faster when people collaborated, when they built on each other's work, when they verified or challenged each other's findings. Competition had its place, but cooperation mattered more. By the mid-1660s, the informal network of natural philosophers Robert belonged to was formalizing. In 1660, a group including Robert had established the Royal Society of London for improving natural knowledge. It was the first scientific society of its kind in England, dedicated to experimental philosophy and the free exchange of ideas. The society's motto was nullius in verba, roughly translated as "take nobody's word for it," evidence over authority, experiments over tradition, verify everything. Robert helped write those principles into the organisation's foundation. The Royal Society gave experimental philosophy institutional legitimacy. It provided a forum where natural philosophers could present their work, debate ideas, and publish findings. It established standards for what counted as reliable evidence. It created a community of people committed to understanding nature through systematic investigation. Robert served on the Society's council. He presented experiments at meetings. He corresponded with members around the world. In 1680, he was offered the presidency. He declined, citing his aversion to taking oaths, a scruple dating back to that thunderstorm in Geneva decades earlier. But he remained deeply involved, shaping the Society's direction and championing its mission. While building institutions and defending experimental philosophy, Robert never stopped investigating specific questions. He studied colour, trying to understand why objects appeared different hues. He experimented with combustion, figuring out what happened when things burned. He investigated the properties of various substances, meticulously recording observations. One experiment involved phosphorus, a newly discovered element that glowed in the dark. Robert obtained a sample and studied its properties obsessively. He burned it, dissolved it, mixed it with other substances. The glow fascinated him. How could something produce light without heat? What did this reveal about the nature of matter and energy? He didn't find complete answers. The full explanation would require understanding chemistry and physics in ways that wouldn't develop for another century. But he asked the right questions. He designed experiments that pushed knowledge forward incrementally. Each observation added a piece to a puzzle he knew he'd never fully solve. His work on respiration was particularly important. Using the air pump, he demonstrated that animals couldn't survive without air. This seemed obvious, but the mechanism wasn't understood. Was air providing something essential, or was it removing something harmful? Robert suspected both might be true, though he couldn't prove it definitively. He was right. Air provides oxygen for metabolism and removes carbon dioxide, but discovering that required tools and concepts that didn't exist yet. What Robert could do was establish that air played a crucial role in respiration, that whatever happened in breathing required some component of air, and that this component was consumed in the process. He showed that a candle flame and a mouse enclosed together died faster than either would alone, suggesting both consumed the same thing from the air. These observations pointed toward oxygen, even though oxygen wouldn't be identified for another century. By 1668, Robert was ready for a change. He'd spent over a decade in Oxford, and while the environment had been productive, he missed London's intellectual energy. More importantly, his sister Catherine needed him. She'd been his closest confidant throughout his adult life, the one person who understood both his scientific ambitions and his religious convictions. Catherine Jones, Viscountess Ranelagh, was extraordinary in her own right. Widowed young, she'd become a political and intellectual force in London. Her home was a salon where philosophers, politicians, and theologians gathered to discuss ideas. She corresponded with major thinkers across Europe. She influenced policy and patronised scholars. When Robert moved into her house on Pall, she had a laboratory built in the garden. For the next 23 years, this would be Robert's base of operations. He worked, wrote, experimented, and received visitors there, while Catherine managed the household and facilitated his connections with London's intellectual elite. Their relationship was remarkable. Catherine supported Robert's work financially and emotionally. She discussed his ideas with him, challenged his thinking, and helped him articulate complex concepts. He relied on her completely, and she on him. Neither married. Both dedicated themselves to intellectual pursuits and religious devotion. Living in London gave Robert access to the Royal Society's meetings and to a constant stream of visitors from across Europe. Natural philosophers travelling through England made it a point to stop at Pall to meet the famous Robert Boyle. He welcomed them, demonstrated experiments, discussed theories, and encouraged their own investigations. He also found time to pursue interests beyond natural philosophy. His religious faith remained central to his life, and he increasingly turned his attention to questions about the relationship between science and religion. Could the two coexist? Did studying nature enhance or undermine faith? These questions mattered deeply to him, and they were becoming urgent as more people worried that the new philosophy threatened traditional Christianity. Robert believed the opposite. Studying nature revealed God's handiwork. The more you understood about how the world functioned, the more you appreciated its design. Natural philosophy and theology weren't enemies. They were complementary ways of understanding creation. This conviction shaped his later work. He began writing books that explicitly connected scientific investigation with religious devotion. He argued that Christians had a duty to study nature, that doing so glorified God, and that the discoveries of natural philosophy supported rather than contradicted Scripture. These weren't casual efforts. Robert poured years into works like The Christian Virtuoso, published in 1690, which laid out his vision of the Christian scientist, someone who investigated nature systematically while maintaining deep faith, someone who saw no contradiction between experimental philosophy and religious devotion, someone who used scientific understanding to enhance rather than replace theological insight. He also funded practical religious projects. In the 1680s, he personally financed the printing of the entire Bible in Irish, both Old and New Testaments. This was unusual. Most English Protestants of his class viewed Irish with suspicion or contempt. Robert saw it differently. If people could read Scripture in their own language, they could develop their own relationship with it. Language shouldn't be a barrier to faith. The project took years and cost a fortune. Robert didn't care. He had money. He had no heirs. And he believed making the Bible accessible mattered more than preserving his wealth. The Irish Bible was printed and distributed, a lasting contribution to Irish culture and Protestant theology. Throughout the 1680s, Robert's health began deteriorating noticeably. His eyesight, already damaged since his illness in Ireland decades earlier, worsened. Reading became increasingly difficult. He relied more heavily on assistants to read aloud to him and to write down his thoughts. His hands trembled. He suffered recurring fevers and episodes of weakness that confined him to bed for days or weeks at a time. But he didn't stop working. The laboratory in Catherine's garden remained active. Visitors continued arriving. Robert continued dictating letters, discussing experiments, planning new publications. He was driven by something deeper than curiosity now. Time was running short, and he knew it. The threat of atheism consumed much of his thinking during these final years. Across Europe, particularly in France, a new breed of thinkers was emerging. They questioned everything, including God's existence. They argued that the universe could be explained entirely through natural causes without invoking divine intervention. Some even suggested that religion was merely superstition, a relic of ignorant times that enlightened people should abandon. Robert found this terrifying, not for himself. His faith remained unshakable, but for others, for society. He believed that without religion, morality collapsed, that people needed to believe in divine judgment to behave ethically, that removing God from the equation would lead to chaos. He also believed these atheists were wrong, fundamentally, demonstrably wrong. The universe couldn't explain itself. The intricate design visible everywhere in nature pointed to a designer. The laws governing matter and motion suggested a lawgiver. Natural philosophy, properly understood, supported rather than undermined faith. So he wrote, book after book defending Christianity against atheist attacks, explaining how scientific discoveries revealed God's wisdom. arguing that the Christian virtuoso, the scientist who maintained deep faith while investigating nature systematically, represented the highest form of intellectual life. The Christian Virtuoso appeared in 1690, one of his most important religious works. It laid out his entire philosophy in a single, extended argument. True knowledge came from studying both God's word in Scripture and God's work in nature. These weren't competing sources of truth. They were complementary. Scripture revealed God's character and purposes. Nature revealed God's power and wisdom. A complete understanding required both. The book addressed specific objections. Some argued that science made God unnecessary. If natural laws explained everything, why invoke a deity? Robert's answer was that natural laws themselves required explanation. Who established these laws? Why did they operate so consistently? The regularity of nature pointed to a rational mind behind it. Others claimed that focusing on material causes diminished God's glory, that explaining how things worked reduced divine mystery. Robert disagreed completely. Understanding mechanism enhanced rather than diminished wonder. Discovering how God accomplished things revealed the sophistication of divine design. A watch was more impressive when you understood its gears than when you simply knew it kept time. He also tackled the accusation that natural philosophers were impious, that their investigation showed disrespect for sacred mysteries. Nonsense. Studying creation honoured the Creator. God had given humans reason and curiosity. Using these gifts to understand the world was an act of worship, not rebellion. The argument was carefully constructed, drawing on decades of experimental work and theological reflection. Robert had spent his entire adult life thinking about these questions. He'd observed nature with meticulous attention. He'd read Scripture constantly. He'd corresponded with theologians and philosophers across Europe. The Christian virtuoso represented the culmination of all this effort. It didn't convince everyone. Some atheists remained atheists. Some religious critics still found natural philosophy suspicious. But the book established Robert as the leading voice for reconciling science and faith. It provided a framework that many Christian scientists would use for generations. Money continued flowing toward religious causes. The Irish Bible Project had been completed, but Robert found other ways to support Christianity. He funded missionary work. He established lectureships at various universities to promote Christian apologetics. He gave money to translate religious texts into languages spoken in places where Christianity was spreading. In 1691, he established what would become known as the Boyle Lectures. He left money in his will to fund an annual series of sermons defending Christianity against atheism and other threats. The lectures were to be delivered by prominent theologians and philosophers in London, and they were to address the intellectual challenges facing the faith. These lectures continue to this day. 3 centuries later, speakers still deliver Boyle Lectures annually, discussing the relationship between science and religion, defending Christian belief, engaging with contemporary challenges. Robert's money, invested wisely, has funded hundreds of lectures by some of Britain's most distinguished thinkers. This was typical of how he used his wealth. He had no children, no direct heirs. His fortune would disperse after his death anyway, so he directed it toward causes he cared about while he was alive: education, religious instruction, missionary work, scientific research, the practical application of Christian principles to real problems. He also worried about his legacy. What would people remember about him? Would they understand what he'd tried to accomplish? Would his books continue being read? Would the experimental approach he'd championed persist? These weren't idle concerns. Many scientific works became obsolete quickly as knowledge advanced. New discoveries replaced old ones, methods improved. What seemed groundbreaking in one generation appeared quaint to the next. Robert wanted his contribution to be lasting, but he knew that scientific progress might render his specific findings irrelevant. What he hoped would endure was the method, the insistence on experimental verification, the careful observation, the mechanical philosophy that explained phenomena through particles and motion rather than occult qualities, the integration of mathematics and measurement into chemical investigation. These principles could outlast any particular discovery, and the religious message that science and faith were compatible, that studying nature was a Christian duty, that understanding mechanism revealed divine wisdom. These ideas mattered more to Robert than any specific experimental result. By 1691, his health had declined severely. He experienced what were probably small strokes, episodes where he lost consciousness or couldn't speak clearly. His strength was failing. He spent most days in bed or in a chair by the fire. Walking became difficult. Even sitting up for extended periods exhausted him. Catherine's health was also failing. She was 75 years old, 3 years older than Robert. She'd been his companion, collaborator, and support for decades. Now, both were approaching the end. Throughout that year, visitors came to Pall to pay respects. Natural philosophers from across Europe made pilgrimages to meet the great Robert Boyle before it was too late. He received them when he could, discussed experiments, offered encouragement, shared thoughts about the future of natural philosophy. He also worked on final revisions to his religious writings. Getting the arguments exactly right mattered. These texts would be his final testimony to the compatibility of science and faith. They needed to be clear, persuasive, unassailable. But he was running out of time. Both of them were. In December 1691, Catherine's condition worsened dramatically. She'd been managing the household from her bed for months, but now even that became impossible. On December 23rd, she died peacefully in her sleep. She was buried at St. Paul's Church in Covent Garden. Robert was devastated. His sister, his collaborator, his closest companion for 30 years. Gone. He'd lost others before. His mother when he was 4, his father when he was 17. But Catherine's death hit differently. She'd been the constant presence in his adult life, the person who understood him completely, the one who made his work possible. He retreated completely after her funeral, stopped receiving visitors, stopped dictating letters. He spent his days in his room, staring at nothing, occasionally asking for scripture to be read aloud. The fight had gone out of him. His own health collapsed rapidly. Whatever had been sustaining him, whatever determination had kept him working through the pain and weakness, disappeared with Catherine. Within a week he was clearly dying. Friends gathered. His remaining siblings came to say goodbye. The household staff prepared for the inevitable. Robert lay in bed, conscious but weak, occasionally speaking but mostly silent. On December 31st, 1691, exactly 1 week after Catherine's death, Robert Boyle died. He was 64 years old. The official cause was likely a stroke, though the records simply note that he died of illness following his sister's death. Grief had finished what disease had started. He was buried in the churchyard of St. Martin in the Fields in London. The funeral was attended by members of the Royal Society, by natural philosophers from across Europe, by friends and colleagues. They eulogized him as the founder of modern chemistry, as the man who'd made experimental philosophy respectable, as a devout Christian whose faith enhanced rather than hindered his scientific work. His will distributed his fortune according to the plans he'd made. Money for the Boyle lectures, bequests to various religious and educational causes, funds for translating and distributing Christian texts, support for missionary work, nothing for family beyond some modest gifts. Everything directed toward advancing the causes he'd devoted his life to. The bulk of his scientific papers went to the Royal Society, where they remain today. His published works, Over 40 books on everything from chemistry to theology to natural philosophy continued circulating across Europe. Some were translated into other languages. Many went through multiple editions. His experimental apparatus, the tools he'd used for decades of investigation, were distributed among his former assistants and fellow natural philosophers. They continued using them, demonstrating his experiments, building on his methods. The impact of his death rippled through the scientific community. The Royal Society held memorial meetings. Natural philosophers across Europe wrote tributes. Publications noted his passing. Everyone acknowledged that an era had ended. The man who defined experimental natural philosophy for a generation was gone. But the work continued. The Royal Society kept meeting. The experimental method kept spreading. The mechanical philosophy kept gaining adherents. The integration of chemistry and physics that Robert had pioneered became standard. The insistence on reproducible experiments and detailed documentation became expected practice. In many ways, his death marked a transition rather than an ending. The foundations he'd laid were solid enough that others could build on them. The questions he'd asked remained open for investigation. The methods he'd developed remained useful. The vision he'd articulated of natural philosophy as a systematic, experimental, mathematical investigation of nature's mechanisms became the dominant approach. What he'd accomplished was extraordinary when you consider the obstacles. He'd transformed chemistry from an obscure art practiced by alchemists into a legitimate science. He demonstrated that systematic experimentation could reveal nature's laws. He'd shown that mechanical explanations could replace occult qualities. He'd proved that mathematics and measurement belonged in chemical investigation, and he'd done all this while maintaining that science and faith were compatible, that studying nature glorified God, that understanding mechanism revealed divine wisdom. This message, so important to him, influenced how many subsequent scientists thought about their work. Not everyone agreed with him, of course. The relationship between science and religion remained contested, still does, but Robert had provided a framework that made it possible to be both a serious scientist and a devout Christian. That combination, which seemed contradictory to some, appeared natural to Robert, and his example inspired countless others who found themselves drawn to both scientific inquiry and religious faith. The next generation picked up where Robert left off, but they didn't always remember why he'd done things the way he had. They inherited the experimental method without always understanding the philosophical commitments that shaped it. They adopted the mechanical philosophy without always grasping the theological framework that made it meaningful to Robert. Take Isaac Newton, for instance. Born the year Robert published The Skeptical Chemist, 20 years younger, but already corresponding with him by the 1670s. Newton read everything Robert wrote about experimental philosophy, absorbed the mechanical approach, built on the corpuscular theory, extended the mathematical treatments of natural phenomena in ways Robert had only begun to explore. But Newton's universe felt different, colder maybe, more mathematical certainly, less obviously the product of divine wisdom. Newton believed in God, wrote more about theology than physics actually, but his natural philosophy functioned independently of those beliefs in ways Robert's never quite did. The split was coming. Science and religion, which Robert had worked so hard to keep unified, were beginning their long divorce. Not immediately, not obviously, but the seeds were planted. By the early 18th century, natural philosophers increasingly described themselves as just that, philosophers, not as servants of God investigating his creation. The language shifted, the motivations changed. What had been a religious duty became professional inquiry. Robert would have been troubled by this, probably, though maybe he'd have recognised it as inevitable. Once you establish that nature operates by mechanical laws, once you insist that experiments replace authority, you've created a system that doesn't require divine intervention to explain daily phenomena. God becomes the clockmaker who wound up the universe and stepped back. Deism, they called it. Not atheism exactly, but not the active, present God Robert believed in either. The Boyle lectures continued, of course, year after year, theologians standing in London churches arguing for the compatibility of science and faith, some of them brilliant, some persuasive, but they were arguing now, defending a position, not simply asserting what everyone already accepted. The chemistry continued too, obviously. Robert's experimental approach became standard practice. His insistence on detailed documentation, reproducible results, mathematical measurement, all of this became foundational. Chemistry departments in universities across Europe taught his methods even when they'd forgotten his name. The air pump experiments inspired generations of pneumatic chemistry. People studied gases, their properties, their behaviours. Joseph Priestley discovering oxygen, Henry Cavendish isolating hydrogen. The whole field of gas chemistry emerged from questions Robert had first asked systematically. His corpuscular theory evolved into modern atomic theory. Not directly, not smoothly. John Dalton in the early 19th century finally provided the mathematical framework that made atomism scientifically rigorous. But he was building on foundations Robert laid. The distinction between elements and compounds that Robert insisted on became absolutely central to chemistry. Lavoisier's chemical revolution in the 1780s depended on clarifying exactly what counted as an element, on establishing that compounds could be broken down into simpler substances, but elements couldn't. Robert had been making this point for over a century. Even his failures proved productive. The search for the philosopher's stone, which Robert never entirely abandoned, led him to investigate chemical transformations with unprecedented rigour. He didn't find transmutation, but he did find countless chemical reactions that nobody had documented before. He discovered new substances, developed new techniques, advanced practical chemistry even while pursuing an impossible goal. His wealth made all this possible. Most natural philosophers of his era were either independently wealthy like Robert or supported by patrons. Science wasn't a profession yet. There were no university positions for experimental chemists, no research grants, no career path. Robert could afford to spend decades on experiments that might lead nowhere. Could afford the equipment, the assistants, the time. This was privilege, obviously. But he used it well. Funded other researchers, published everything, made his findings freely available rather than hoarding them as trade secrets. The Royal Society's commitment to open publication of results owed much to Robert's example. The whole structure of modern scientific communication, journals publishing detailed experimental reports, traces back to practices he helped establish. Though communication was frustratingly slow. Letters took weeks to reach correspondents in other countries. Publications took months or years to circulate. Debates dragged on because responses couldn't arrive quickly. The pace of progress depended partly on the speed of horses and ships. Robert's correspondence network spanned Europe. He wrote to natural philosophers in France, Italy, Germany, the Netherlands, shared results, asked questions, proposed collaborations. This web of relationships accelerated discovery in ways that wouldn't have been possible if everyone worked in isolation. Some of his correspondents were Catholics, which was unusual for an English Protestant in this period. But Robert cared more about someone's experimental work than their theology. If they were doing good science, he'd engage with them. This wasn't universal tolerance exactly. He still believed Protestantism was correct, but he could separate scientific merit from religious affiliation in ways many contemporaries couldn't. His influence extended beyond natural philosophy into medicine. Though he never practiced medicine formally, his chemical investigations suggested new approaches to understanding disease and treatment. The iatrochemical school of medicine, which tried to explain bodily functions through chemical processes, drew heavily on his work. He investigated the medicinal properties of various substances, tested remedies, documented results. Some of his findings were valuable, others were wrong, but the method, chemical analysis, applied to medical questions, pointed toward modern pharmacology. His air pump experiments had medical implications too. Understanding respiration, the role of air in sustaining life, these questions connected directly to health. Physicians began thinking about breathing as a chemical process rather than merely a mechanical one. The relationship between science and medicine remained close throughout this period. Most natural philosophers had medical training. Most physicians were interested in natural philosophy. The boundaries between fields were porous. Robert embodied this interconnection. Never quite a physician, but deeply engaged with medical questions. Never quite a pure theorist, but always interested in practical applications. His theological writings continued finding readers long after his death. Some were reprinted multiple times, translated into other languages. The Christian virtuoso particularly remained popular. The argument that science enhanced faith rather than undermining it spoke to people anxious about the direction natural philosophy was taking. But even here, the context was shifting. Robert had written assuming his readers shared his faith and needed reassurance that science was compatible with it. Later readers increasingly needed persuasion that faith was compatible with science. The burden of proof had reversed. The Irish Bible project he'd funded continued distributing copies for decades. Whether it accomplished what he hoped, spreading Protestant Christianity among Irish Catholics, is debatable. The linguistic preservation was valuable regardless. These were among the first printed Irish language Bibles, documenting the language at a crucial period. His will's provisions for supporting missionary work funded various projects, some successful, others less so. The colonial and cultural assumptions underlying much missionary work of this era are obvious now, in ways they weren't then. Robert genuinely believed he was supporting the spread of truth. That belief was sincere, even if the implementation was often problematic. The question of Robert's legacy is complicated by what came after. He'd hoped to demonstrate that natural philosophy and Christian faith were mutually reinforcing, that studying nature revealed divine wisdom, that mechanical explanations enhanced rather than replaced theological understanding. Did he succeed? Partly. For a generation or two, many natural philosophers accepted this framework. They saw themselves as investigating God's creation. Their work had religious significance, but the trajectory of science moved away from this position. Not universally, not immediately, but steadily. By the 19th century, most scientists saw their work as independent of religious considerations. Some were believers, some weren't, but the science itself didn't require faith. This wasn't Robert's fault. He couldn't have prevented it. The commitment to natural explanations, to mechanical causes, to mathematical laws, these principles he championed inevitably led to a more secular science. Once you establish that nature operates according to discoverable laws, you've created a system that functions without constant divine intervention. Robert had believed those laws reflected divine wisdom, that discovering them glorified God. But the laws themselves, once discovered, worked regardless of what anyone believed about their ultimate source. The mechanical philosophy he advocated became mechanism, a worldview that explained everything through matter and motion. No vital forces, no occult qualities, no mystical influences, just particles interacting according to mathematical laws. This was powerful. It enabled unprecedented scientific progress, but it also made nature feel less obviously the product of intentional design. The clock metaphor worked too well. Once you accepted that the universe ran like clockwork, the clockmaker's ongoing presence became unnecessary to explaining its operation. Robert had tried to keep both, the mechanical laws and the divine lawgiver, the natural order and the supernatural creator. For him, these weren't separate. Studying one revealed the other, but holding both together required constant effort, required insisting that mechanism didn't exclude meaning, that mathematical laws didn't eliminate purpose, that scientific explanation and theological significance operated on different levels. Not everyone made that effort. Easier to focus on the science and leave theology aside, not reject it necessarily, just treat it as separate, distinct domains that didn't intersect. This separation, which Robert had resisted, became standard. Science dealt with how nature worked, religion dealt with why it mattered. The two rarely engaged directly. Whether this was progress or loss depends on your perspective. Science certainly advanced faster once it stopped worrying about theological implications, but it also lost something Robert considered essential: the sense that investigating nature was inherently meaningful. That understanding mechanism revealed purpose. His experimental method survived intact. His theological integration didn't. We inherited half his vision, the part that produced results, the part we could measure and verify, the part that scaled. Robert probably would have been disappointed by this. He'd spent his life arguing that you couldn't separate the two, that science without faith was incomplete. That understanding nature required acknowledging its creator. But he also would have recognized the value of what survived. The experimental method transformed human understanding of the world. The insistence on evidence over authority enabled progress he couldn't have imagined. Chemistry became a rigorous science. Physics developed mathematical precision. Medicine moved beyond ancient theories toward evidence-based practice. All of this built on foundations Robert helped establish. His corpuscular theory wasn't quite right. Modern atomic theory is more sophisticated, but he was pointing in the right direction. Matter is made of particles. Their interactions explain chemical change. The details were wrong, but the framework was sound. His gas laws were correct as far as they went. Later discoveries refined them, added temperature relationships, developed more complete equations, but the basic insight held. Pressure and volume relate inversely. That's still true, still taught, still called Boyle's law. The distinction between mixture and compound that he insisted on remains fundamental. We understand it better now, know the mechanisms, can explain it at the atomic level. But the conceptual difference he identified was real. Even his theological work had lasting impact, though not always in ways he intended. The natural theology tradition, arguing from nature's design to a designer, continued for centuries. William Paley's watchmaker argument in the early 19th century echoed Robert's approach. The argument eventually faced serious challenges from evolutionary theory, but it shaped how generations thought about the relationship between science and faith. The Boyle lectures continued until 2004, over 300 years of annual sermons on natural theology and religious philosophy. The endowment Robert created kept functioning long after anyone remembered why he'd established it. That's a different kind of legacy, not direct influence but sustained institutional presence. Robert's life demonstrates something important about how scientific progress happens. It's not purely rational, not just evidence and logic. It's also motivated by deeper commitments. For Robert, that motivation was religious. He investigated nature because he believed it revealed divine wisdom. Others have been motivated differently: curiosity, ambition, the pleasure of solving puzzles, the desire to improve human welfare. The motivation doesn't determine the science's validity, but it affects what questions get asked and how persistently they're pursued. Robert asked questions about air because he believed understanding God's creation was a duty. Someone else might have asked them from pure curiosity. The experiments would be the same, the results would be the same, but the driving force was different. This matters because science requires sustained effort, decades of work sometimes, failed experiments, dead ends, frustration. You need something pushing you forward. For Robert, that something was faith. The belief that this work mattered ultimately, not just practically. Modern science has largely abandoned that particular motivation, but it needs something in its place, some reason why this work matters beyond next year's publications or funding cycles, some framework for meaning. Robert provided one answer, not the only answer, maybe not even the best answer for everyone, but an answer that worked for him and enabled extraordinary productivity. His legacy is the experiments he performed, the methods he developed, the questions he asked. It's also the example of someone who took science seriously because he took faith seriously, who saw no contradiction between investigating nature rigorously and believing in God deeply. Whether that integration remains possible is still being debated, but Robert proved it was possible for him in his time. And that possibility continues inspiring people who find themselves drawn to both scientific inquiry and religious faith. The question isn't whether that integration is still possible. The question is what Robert's actual daily life looked like in those final London years. Because the image of the pious scientist peacefully conducting experiments doesn't capture the reality. He was sick, constantly. His eyes had deteriorated to the point where he could barely read. Everything had to be read aloud to him by assistants. His hands shook. Writing was difficult, so he dictated his thoughts to secretaries who struggled to keep up with his tangential thinking. He had respiratory problems that left him gasping for air. Ironic for someone who'd spent decades studying air. He obliged when he could, but the constant stream of visitors made it difficult to focus on his work. Scholars, politicians, religious figures, everyone wanted to meet the famous Robert Boyle. He obliged when he could, but the constant interruptions exhausted him. He needed quiet to think, solitude to work, but solitude was rare in a house that functioned as London's intellectual crossroads. His laboratory was in the back garden, a separate building where he could escape, but even there assistants came and went. Experiments required help, equipment needed maintenance, and Robert's declining health meant he couldn't do everything himself anymore. He directed, others executed. It wasn't the hands-on work he'd loved at Oxford. Money remained a problem despite his wealth. His Irish estates generated income, but irregularly. Rents came late or not at all. Managing property from London was difficult. He had stewards, but they needed oversight. Legal disputes arose constantly. Tenants complained. Boundaries were contested. Robert hated dealing with it, but had no choice. And he was generous, too generous according to some. He gave money to scholars who needed it, funded publications, supported charitable causes. The Irish Bible translation cost him thousands of pounds. The Boyle Lectures endowment was substantial. He lived comfortably, but not extravagantly, channeling most of his wealth into projects he considered important. His religious doubts never fully disappeared. He wrote about them obliquely in his later works. The certainty he projected publicly masked ongoing internal struggles. He believed in God, he believed in Christianity, but specific doctrinal questions troubled him. Predestination versus free will, the nature of salvation, the problem of evil. These weren't abstract theological puzzles, they were personal concerns. He dealt with them through work. When doubt crept in, he threw himself into experimentation. The physical world was knowable in ways theology wasn't. You could test hypotheses about air pressure. You couldn't test theories about grace. Science provided certainty, or at least provisional certainty, the kind you could build on. But science also raised new theological problems. The mechanical philosophy he advocated explained natural phenomena through particles and motion. No need for supernatural intervention in everyday events. God created the universe and its laws, then stepped back. This was deism's direction, though Robert would have rejected that label. He believed God remained active in the world. But how? through miracles that violated natural law, through providence working within natural law. The distinction mattered, and he never fully resolved it. His correspondence during these years reveals the complexity. Letters to friends mixed scientific observations with theological reflections. A paragraph about phosphorescence followed by speculation about angels. Discussion of chemical reactions interrupted by worries about the immortality of the soul. His mind didn't compartmentalize. Science and religion interpenetrated constantly. This drove some correspondents crazy. They wanted clear boundaries. Talk about science in one letter, theology in another. Robert couldn't do that. For him, it was all connected, all part of understanding God's creation. Separating them would have been artificial, dishonest even. The Royal Society meetings provided structure. He attended when his health permitted, watched demonstrations, listened to reports, occasionally presented his own findings, but he was no longer at the centre of innovation. Younger members were pushing new directions. His great work was behind him. This bothered him less than you'd think. He'd never sought fame for its own sake. Recognition was nice, but not essential. What mattered was whether the work was done, whether natural philosophy advanced, whether God's wisdom in creation became more apparent. If others accomplished that, fine. He didn't need to be the star. But he did want to be remembered correctly. Hence the autobiographical fragments, the careful curation of his papers, the instructions to friends about how his work should be presented after his death. He knew he'd be judged by history, wanted to shape that judgment, not from vanity, but from concern that his religious motivations be understood. He feared being remembered as just a scientist, when for him, the science was always in service of something larger. Catherine understood this better than anyone. They'd lived together for decades by this point. She knew his moods, his anxieties, his patterns of thought. When he spiraled into doubt, she pulled him back. When he overworked himself into illness, she forced rest. Their relationship was the anchor of his later life. She was also intellectually formidable in her own right. They discussed philosophy, theology, politics. She had connections throughout London's elite, knew everyone worth knowing, provided Robert with information and introductions he couldn't have obtained otherwise. Her salon was partly for him, creating an environment where he could engage with the best minds without leaving home. The sibling bond was unusual for its depth and duration. Most aristocratic siblings went their separate ways after childhood. Marriage, inheritance, geography pulled families apart. Robert and Catherine reversed this, grew closer with age, built a shared life that sustained both of them. Neither married. Robert never showed interest despite family pressure early on. Catherine had married young, but her husband was largely absent and they'd effectively separated. So they created an alternative household structure, two unmarried siblings making a life together. It worked because they genuinely liked each other, shared interests, complementary temperaments. When Catherine's health began failing in late 1691, Robert was devastated. He'd always been the sickly one. She'd been the strong one. The reversal was unthinkable. He sat with her constantly, read to her, prayed with her, watched her decline. She died on December 23rd, 1691. He was at her bedside. The loss was profound. Not just emotional, but practical. She'd managed the household, handled correspondence, shielded him from interruptions. Without her, the infrastructure of his life collapsed. He followed 8 days later, December 31st, 1691. Whether grief accelerated his death or it was simply coincidence, we can't know. But the timing suggests they were more intertwined than even their contemporaries realised. Two lives so connected that one couldn't continue without the other. His funeral was modest by aristocratic standards. He'd specified no elaborate ceremony, no long eulogies, simple burial in St. Martin in the Fields. The Royal Society sent representatives, Friends attended, but it wasn't a major public event. He wouldn't have wanted that. The estate was complex. Properties in multiple countries, investments in various ventures, the Boyle Lectures endowment to be established, literary executors to sort through thousands of pages of manuscripts. It took years to settle everything. Disputes arose, some papers disappeared, others were published against what might have been his wishes. His reputation immediately began shifting. The next generation focused on his scientific contributions. The theological works were acknowledged but downplayed. By the 18th century, he was remembered primarily as a natural philosopher. The religious dimension that had been central to his self-understanding became a footnote. The Enlightenment needed him as a precursor, a founder of experimental science, someone who'd helped break free from scholastic philosophy. Emphasizing his piety complicated that narrative, so it was minimized. Not denied, but de-emphasized. He became a scientist who happened to be religious rather than a religious man who did science. This persisted for centuries. Victorian scientists claimed him as one of their own, someone who'd helped establish science's independence from theology. The irony would have amused Robert. He'd spent his life arguing they were inseparable, but history rewrote him to fit its needs. Modern scholarship has corrected this somewhat, recognizing that for Robert, the religious motivation was primary. The science served the theology as much as the theology served the science. You can't understand his work without understanding his faith. They weren't separate domains. They were unified by his conviction that studying nature glorified God. This makes him harder to categorize, harder to claim for any single tradition. Scientists want him as a founder of experimental method. Christians want him as proof that faith and science aren't opposed. Historians want him as evidence of the complexity of the scientific revolution. Everyone's right, and everyone's oversimplifying. What if we just let him be complicated? A man who believed deeply in God and deeply in experimental investigation, who saw no contradiction because for him there wasn't one, who produced lasting scientific work while maintaining sincere religious commitment, who struggled with doubt while projecting certainty, who was generous and petty, brilliant and stubborn, innovative and traditional. The real Robert Boyle was all of these, not a simple icon, but a complex human being, trying to make sense of the world through both reason and faith, sometimes succeeding brilliantly, sometimes failing completely, always trying, always believing the effort mattered. Money troubles, who gossiped about money troubles, who gossiped about colleagues, who worried about his legacy, who experienced doubt and fear and loneliness, who found meaning in work when personal relationships disappointed. The manuscripts show constant revision, crossing out, starting over, changing his mind. This wasn't effortless genius. It was hard work, sustained effort over decades, success built on countless small failures that never made it into published works. And the religious writings show someone wrestling genuinely with difficult questions, not performing piety for an audience, but actually trying to understand, to reconcile what he observed in nature with what he believed about God, to find coherence where others saw contradiction. He didn't always succeed. Some of his arguments don't work. Some of his theological positions were questionable, even by his own era's standards. But the attempt was sincere. He wasn't using religion as window dressing for science or science as apologetics for religion. He was genuinely trying to hold both together, to let each inform the other, to find truth wherever it appeared. Showed it was possible to take both, seriously, to be rigorous in both domains, to refuse the easy path of separating them completely. Modern debates about science and religion often assume they're inherently opposed, that you must choose between them, that serious scientists can't be serious believers, and vice versa. Robert's life contradicts this, not by providing easy answers, but by demonstrating that the relationship is complicated. That integration requires work, that it's possible, even if difficult. Whether his specific integration remains viable is debatable. His theological framework was Protestant, his science was pre-Newtonian. Both have been superseded in various ways, but the attempt itself, the refusal to abandon either domain, still resonates, still offers something to people navigating similar tensions today. The final decades brought health problems that would have ended most careers. His eyes continued deteriorating. Reading became nearly impossible without assistance. He hired secretaries to read aloud while he listened, to write for him when his hands shook too badly. The strokes came periodically, each one taking something: mobility, clarity, energy. But he kept working, kept experimenting, kept writing. The productivity was remarkable considering the physical limitations. Books kept appearing, treatises on medicine, on the relationship between science and scripture, on the mechanical philosophy, on colours, on cold, on nearly everything that interested him. Some were brilliant, others repetitive, a few confused, but he couldn't stop. Work was identity, purpose, meaning. What else did he have? Catherine remained his anchor, her home his refuge, her support unwavering. When he was too ill to leave his room, she brought visitors to him. When experiments failed, she listened to his frustrations. When doubt crept in, she reminded him of his calling. Their relationship was the most stable thing in his life, more constant than any friendship, more intimate than most marriages, though it was neither. Just two people who understood each other, who shared values and interests, who made each other's lives better through proximity. In 1680, the Royal Society elected him president, the highest honour they could offer. He declined, not from modesty, from principle. The position required taking oaths, swearing allegiance, making promises in God's name. That storm in Geneva decades earlier still haunted him. He'd sworn never to swear oaths, and he meant it, even when refusing cost him prestige, even when colleagues were baffled. The conviction ran too deep to compromise, so he remained a council member, contributing without leading, influencing without controlling. Probably more effective that way. Presidents deal with administration, politics, fundraising. He could focus on actual science, on reviewing papers, on conducting experiments, on being useful rather than ceremonial. The 1680s brought increasing isolation. Many contemporaries had died. Hooke was still around, but their relationship had soured. Scientific disputes, personality clashes, the usual academic drama. Newton was rising, but they never became close. Different temperaments, different approaches, mutual respect without friendship. Locke remained in contact but was often abroad, busy with his own work, his own controversies. The circle of intellectual equals shrank, leaving Boyle increasingly alone at the centre of a world he'd helped create. He funded religious projects, paying for Bible translations, supporting missionaries, establishing lectures to defend Christianity against atheism. The Boyle lectures would continue for centuries, still exist today, a permanent institution promoting natural theology, arguing that reason and revelation align, that science supports faith. It was his attempt at lasting impact beyond his own writings, a structure that would continue the work after he was gone. In 1691, Catherine fell ill, seriously this time. Not the usual complaints, but something fundamental failing. She was 83. He was 64. Both had outlived most of their generation. But this was different. This was losing the person who'd made everything possible. He visited her sickbed daily, sat with her, talked when she could, just stayed present when she couldn't. Watching someone die slowly is its own kind of torture, especially someone you need, someone whose existence makes yours bearable. She died on December 23rd, 1691, a week before Christmas, The household went into mourning. But for Robert, it was more than grief. It was the foundation collapsing. The structure supporting his life suddenly gone. He'd lived in her home for 30 years, worked in her garden laboratory, relied on her in ways he'd never articulated, and now she was gone. He didn't recover. Couldn't. The illness that killed him started within days. Whether grief triggered it or just coincidence, we don't know. But the decline was rapid. His body had been failing for years. Now it simply gave up. He died on December 30th, 1691, 1 week after Catherine, like he'd been waiting just long enough to see her properly buried. Then decided there was no point continuing. They were buried separately, she in her parish church, he in St. Martin in the Fields. But the timing suggests a connection deeper than logistics. Two lives so intertwined that one couldn't outlast the other long. His will distributed wealth carefully. Bequests to servants, to poor relatives, to causes he'd supported. The Boyle lectures received endowment. He wanted nothing wasted, everything too. He wanted nothing wasted, everything to serve the advancement of knowledge. The memorial in the church called him a great natural philosopher, a devout Christian, a generous benefactor, standard language, true but generic. It didn't capture the contradictions, the complexity, the ways he was difficult and brilliant and frustrating and innovative, just presented a simplified version, the one that fit on monuments. His reputation evolved over centuries. Initially remembered primarily as a chemist, the man who established that air had weight and elasticity, who developed the law relating pressure and volume, who wrote the Skeptical Chemist. That was the core. The 18th century emphasized his mechanical philosophy, his corpuscular theory, his rejection of Aristotelian elements. He became a transitional figure, moving chemistry from alchemy toward science, from mysticism toward mechanism. That narrative fit Enlightenment values: rational, progressive, modern. The 19th century noticed his religious writings more. Victorian scientists uncomfortable with pure materialism found him useful. Look, a rigorous experimenter who was also devout. Proof that science and faith weren't incompatible. He became ammunition in cultural debates, evidence for whichever side could claim him most convincingly. The 20th century brought more critical analysis. Scholars examined what he actually did versus what he claimed. Found gaps, inconsistencies, experiments that didn't quite prove what he said they proved, arguments that were less rigorous than they appeared. He became more human, more fallible, more interesting. Current historians see him as embedded in his context. Not a modern scientist born early, but a 17th century natural philosopher, working within assumptions we've abandoned, asking questions we no longer find relevant. Successful by his era's standards more than ours. The science that survived is real but limited. Boyle's law remains valid within its parameters, a genuine contribution, permanently part of chemistry. But much of his work has been superseded. Better experiments, better theories, better understanding. That's how science works. You're not supposed to be right forever. You're supposed to advance knowledge incrementally. The religious writings haven't fared as well. His natural theology assumes a mechanical universe created by a rational God. Both assumptions are harder to maintain now. The universe appears more complex than clockwork, the relationship between natural order and divine purpose less obvious. His arguments don't convince modern readers the way they convinced contemporaries. Too much has changed, but the attempt still matters. The effort to integrate, to hold multiple frameworks simultaneously, to refuse easy compartmentalization. That's relevant regardless of whether his specific integration works. We still argue about science and religion, still try to reconcile different ways of knowing, still need examples of people who took both seriously, even if their solutions don't transfer directly. What remains most striking is the scope. The sheer range of what he attempted, chemistry and medicine, and theology, and philosophy, and biblical translation, and mechanical design, and natural history, and more. He wanted to understand everything, or at least contribute to understanding everything. That ambition is almost quaint now. We've accepted that knowledge is too vast for any individual to master. Specialization is inevitable, necessary, but something's lost in that acceptance. Boyle believed you could hold it together, that chemistry informed theology, and theology informed chemistry. That studying nature revealed God, and understanding God illuminated nature. That it all connected. He was probably wrong about the specifics, but maybe right about the principle. That knowledge fragments at our peril. That the boundaries between disciplines are artificial. That seeing connections matters as much as developing expertise. His legacy is complicated by what he represents to different groups. Scientists claim him as a founder. Christians claim him as a defender of faith. Historians claim him as evidence of complexity. Everyone's using him, turning him into a symbol rather than a person. The real Boyle was messier, more contradictory, less useful as an icon. He was brilliant and petty, generous and status-conscious, innovative and traditional, certain and doubtful, successful and frustrated, all of that. Not a simple story, not a clear moral, just a life, lived intensely, directed toward goals that mattered to him, achieving some, failing at others, leaving behind work that outlasted him, but also leaving questions about what he really believed, about how he reconciled contradictions, about whether the integration he claimed was genuine or performed. We can't know. The interior life is lost, only the public record remains, and that record is carefully constructed, designed to present a particular image. We can analyse it, question it, but we can't get behind it to the actual person. Maybe that's true of everyone. The historical record is always incomplete, always filtered, always shaped by what got preserved and what didn't. But with Boyle, the gap feels especially large between the controlled public presentation and whatever was actually going on inside. The final assessment depends on what you value. If you care about specific scientific contributions, Boyle's law matters. The pneumatic experiments, the corpuscular theory, real advances that shaped subsequent work. If you care about methodology, his emphasis on experiment and replication matters. His detailed reporting, his public demonstrations, his attempt to make natural philosophy verifiable. If you care about cultural impact, his role in establishing the Royal Society matters. His influence on how science was done. His example of what a natural philosopher should be. If you care about science-religion dialogue, his attempt at integration matters. His Christian virtuoso, his natural theology, his insistence that both domains deserved serious attention. All of those are legitimate. All of those are real. He contributed to all of them. But none captures everything. None explains the whole person. The man who lived in his sister's house for 30 years, who never married, who struggled with illness, who worked obsessively, who left behind thousands of pages, who died a week after the person who mattered most. That person remains elusive, hidden behind the work, behind the reputation, behind the historical interpretations. We know what he did, we know what he wrote, we know what others said about him, but we don't really know him. And 4 centuries later, that's probably permanent. The evidence won't improve, the questions won't be answered. We're left with the work and the legacy and the endless interpretations, with the fact that he mattered, that his contributions were real, that his influence extended far beyond his lifetime. That's more than most people get, more than most people leave behind. A name that's remembered, work that's still cited, ideas that shaped how we think, even if we've moved beyond them, even if we question them, even if we complicate them. He's still there, still part of the conversation, still relevant somehow. Not as an icon, not as a simple story, but as a reminder that knowledge is built by actual people, complicated people, flawed people, people trying their best with limited understanding, people getting some things right and other things wrong, people whose work outlasts them even as the person fades into history. That's Robert Boyle, chemist and theologian, experimenter and theorist, brilliant and limited, remembered and forgotten, present and absent, still here somehow, still mattering, still asking us to figure out what we think about science, about faith, about knowledge, about truth, about how to hold it all together, or whether we even should. He's gone now, both of them, 8 days apart in December 1691. Catherine first, then Robert. The house on Pall Mall empty of the two people who'd filled it with conversation, and experiment, and purpose for 3 decades. London barely noticed a few obituaries, a modest funeral. The Royal Society marked the loss, held memorial meetings, spoke respectfully about contributions, then moved on. There was always more work to do, more experiments to conduct, more questions to answer. The world Robert left behind was different from the one he'd entered. Not because of any single discovery, not because Boyle's law changed everything or the Skeptical Chemist revolutionized chemistry overnight, but because the method had taken root. The idea that you could interrogate nature systematically, that evidence mattered more than authority, that experiment revealed truth in ways speculation couldn't. He didn't invent that idea. Galileo was doing it before Robert was born. Francis Bacon had articulated the principles. Others were experimenting across Europe. But Robert made it respectable, made it systematic, made it something educated gentlemen could pursue without apology. The Royal Society embodied this transformation, an institution dedicated to experimental philosophy, publishing results, maintaining standards, creating community among people who shared the conviction that nature could be understood through careful observation and measurement. Without Robert, would it have happened anyway? Probably. The intellectual currents were moving that direction regardless. But he accelerated the process, demonstrated what was possible, provided an example others could follow. His religious integration didn't survive, that's clear now. The vision of science as glorifying God, of mechanism revealing divine wisdom, of natural philosophy as a form of worship. It lasted maybe 2 generations after his death, then fractured. Science and religion didn't become enemies exactly, but they stopped being the unified project Robert had believed in. The Boyle lectures continued. Yes, still do, but they became defensive, arguing for compatibility rather than assuming it, responding to challenges rather than confidently asserting that studying nature revealed God's character. The burden of proof shifted. Was Robert naive, believing integration was possible? Maybe. Or maybe he understood something we've forgotten. That separating how from why, mechanism from meaning, facts from values, costs something.